Ladies and gentlemen, please welcome Melis Landau.
So, good morning, everybody. Thank you to the organizers for this invitation. So this talk is the first talk of the session on the core and the dynamo. So before presenting my own research, I will first give a broad introduction on the topic, and I will try to connect the different talks that we'll hear in the next hour or so. The theme that connects the sessions today is habitability. And one ingredient that makes the Earth a habitable planet is the geomagnetic field. So it protects us and our atmosphere from the solar wind, and it helps us to navigate, or we have long used it to navigate on oceans, and we use it today to navigate in space. And many other species, like salmons, can actually feel the magnetic field, and they use it to migrate over long distances. And even in the distant past, we find in the geological record, we find evidence for magnetotactic bacteria. And here you have, you have a movie that was taken by the group of Alex Petrov in Clark University, which is not going to work, which is actually showing bacteria under a magnetic field, and the direction of the field is shown by the red arrow. And I wonder how I can actually play this movie, because I don't have... It's going to be a bit of... So can the technician press enter on the computer, for instance? Okay, well, there will be no movie. So basically what you were supposed to see is that those bacteria moves along the magnetic field line, and when they change the magnetic field direction, the bacteria moves in the direction of the field. So the magnetic field is important for life, and so the next question is, where does the magnetic field come from? And you all know the answer. It comes from flow motions in the Earth's core, and that's what we call the dynamo effect. And the dynamo effect was actually proposed precisely 100 years ago by Lagroix. So today we celebrate the 100 years of AGU, but we could also celebrate, or we can also celebrate, the anniversary of this great hypothesis by Lagroix, which we call the geodynamo. Let's imagine we are in 1919. What would we know about the core? We basically knew very little. We knew that there was a core, and we knew where the core mantle boundary was. But there were only speculations that the core was made of iron, and we didn't know that there was a liquid outer core, a solid inner core. We didn't even know whether the Earth was 100 billion years old or billion of years old. So 100 years later, what do we know? We know that the Earth and the Earth's core formed 4.5 billion years ago. And during this process, the Earth accumulated a huge amount of heat. And this heat is still escaping today from Earth. And so the outer liquid core cools down and progressively solidifies to form the inner core. As this happens, light elements are released, and this generates convection and magnetic field generation in the Earth's core. And so today, we have very precise global maps of the magnetic field, of the geomagnetic field, and we'll hear more about those in the talk by Monica Corte. We also have numerical simulations that can model convection and dynamo action in the outer core. And those simulations reproduce a magnetic field that very much look like the Earth's magnetic field. So we'll hear more about those simulations in the talk by Philippe Cardin. Other constraints come from paleomagnetism. We'll hear about these in the talk by Claire Nichols. And for instance, we know from the magnetization of ancient rocks that the geodynamo has been active, or was active, 3.4 billion years ago. And this has huge implications for the core, because at that time, there was probably no inner core, and so a big question is what powered the geodynamo then? One possible mechanism is that as the core cools down, magnesium and or silicon are exsolved from the core, and this can power convection and dynamo action. And so we'll hear more about this mechanism in the talk by Sarah Arveson and Kay Hirose. But for this mechanism to work, you need to put a lot of magnesium and silicon in the core initially. And the initial composition of the core depends on the processes that form the Earth. So in the next part of this talk, I will talk about core formation and how this determines the composition of the core. So core formation is a topic I've worked on for the past 5 years or so with a number of co-authors who are listed here. So the first question is, what do we know about core formation? The main constraints come from geochemical data. Extinct radioactivity, for instance, tell us that the core formed in less than 100 million years. And the partitioning of elements between the core and the mantle depends on pressure and temperature. Therefore, the composition of the core and the mantle give us information about the depth and the temperature of core-mantle differentiation. However, to obtain the values that I show on the right, you need to make assumptions about the physics. First, you need to know the partition coefficient between the core and the mantle, and that comes from mineral physics. And second, you need to know the degree of equilibration between the core and the mantle. By that I mean what fraction of the core and what fraction of the mantle mixed and equilibrated together. And so this is a mixing problem, so it's a question that belongs to fluid dynamics. And the goal of my work is basically to understand the fluid dynamics of core formation in order to constrain the degree of chemical equilibration between the core and the mantle. And this is very important because the interpretation of geochemical data depends a lot on the degree of chemical equilibration. To demonstrate this, I will take the example of extinct radioactivity using hafnium tungsten. And so here we define a degree of equilibration so that this degree of equilibration on the top right takes a value equal to 1 when the entire core equilibrates with the entire mantle, so there is full equilibration, and it's equal to 0 when there is no equilibration. And on the figure on the left, you see the x-axis corresponds to the duration of core formation deduced from hafnium tungsten, and the y-axis corresponds to the degree of chemical equilibration. And so you see that if the degree of equilibration is equal to 1, you get a duration of core formation about 15 million years. But now, if you don't know the degree of equilibration anymore, the duration of core formation extends or takes value between 15 million years to hundreds of million years. And so to interpret geochemical data, you really need to know the value of this chemical equilibration. So how can we determine this? So we know today that much of Earth's mass formed by large impacts that involved an impactor and a proto-Earth, which probably were both differentiated into a core and a mantle. During each of these impacts, shock waves are liberated, and so shock waves melt the impactor and a portion of the proto-mantle. And so just after the impact, the core of the impactor is released in a pool of liquid silicates that we call the magma ocean. And those processes happen in very turbulent conditions. And so because you have turbulence, you can mix metal and silicates. And if you have mixing between metal and silicates, you increase the surface area between the two phases, and you favor chemical transfer. So if you want to predict chemical equilibration, we need to predict the degree of mixing between metal and silicates. And so our objective here is to quantify mixing between metal and silicates during and after the impacts that form the Earth. How can we do this? So the most common tool, as we hear in the previous hours, the most common tool to study impact are numerical simulations, as the one I show on the top of the slide. And these simulations indicate that the impactor core migrates with the core of the Earth in about a few hours. So it's very quick. But the resolution in those simulations is of about 100 kilometers. And we know that chemical equilibration, chemical transfers, are efficient on a length scale of 1 centimeter. So those simulations cannot quantify chemical equilibration, and we need something else. And actually, it's easier to produce small scales and turbulence in the lab. So this is the approach we take. And of course, you cannot reproduce the giant impacts that form the Earth in the lab. So instead, we build analog systems. And I'm going to show you one example, so one series of experiments that I have done recently. So in those experiments, we focus on the impact of a liquid volume with another liquid. The impactor is a salt solution, and it represents the impactor core, and it impacts a pool of water that represents the magma ocean. So the impactor impacts the water and mixes with the water. And here, our impactor is denser than the water, and we also put dye in the impactor to follow mixing. So our objective is to quantify mixing during these experiments. So here, I'm basically pretending that in my 70-centimeter tank, I can model the impact that form the Earth. So how is it possible? To do this properly, we actually rely on dimensionless numbers. So first important dimensionless numbers here is what we call the Reynolds number, which is the ratio between inertia and viscosity. And during core formation, this number was extremely large. So we cannot reproduce this in the lab, but we know from the literature in fluid dynamics that if the Reynolds number is above a few hundreds, then mixing is independent of the Reynolds number, and you reach what we call a turbulent regime. And so in our experiments, we managed to be in this turbulent regime. So we think we are in the right dynamical regime. And in passing, you can see that impact simulation cannot reach this turbulent regime, and that's why they cannot produce small scales. So now, the main control parameter that will come back later is what we call the Froude number, which is the ratio between inertia, the inertia of the impact, and gravity. So it depends on the impact velocity u, which is in the nominator here. So our objective is to vary this number and to quantify mixing as a function of this number. So first of all, what does it look like? So this is not going to play. That's a bit of a pity. So this was playing fine in the speaker ready room, of course, but now it's not. So it's a bit frustrating because it's going to be difficult for me to describe these experiments. Anyway, so my point here was that the experiment very much looked like what you get in numerical simulation, which is on the right of this slide. And what you were supposed to see in this movie is that actually in our experiments we can also produce small scales, and so we think we can quantify mixing. And that's something that you are going to see at least in the next slide, because those are pictures. So here you see what an experiment looks like as a function of time. And so what we observe is that in our experiment, mixing happens in two main stages. The first stage corresponds to the impact that you see on the left. And if we wait long enough, because the impactor is denser than the water pool, it forms a plume that sinks into the tank and reaches the bottom of the tank. And so in our previous work, we showed that we can quantify mixing during the plume stage. And we show that during the plume stage, mixing depends on the initial size of the plume that you can see here in red. But here I show an experiment at quite low impact velocity, so low Froude number. If now I add an experiment at much higher Froude number, so higher impact velocity, you see that we get the volume of the plume is much larger. And so if the plume is much larger, that means that the impactor has entrained more ambient fluid. So what we want to do here is basically to quantify this entrainment. Can we quantify the volume of entrained fluid as a function of the Froude number? And we can do that using basically those images. We can take those images and derive or estimate the volume of the plume. From this, we subtract the initial volume of the impactor to estimate the volume of entrained liquid. And so we do that in all our experiments, and we find a scaling law as a function of the Froude number. So now, if we extrapolate to planetary impacts, that means that we can actually predict the volume of entrained fluid, which represents the volume of silicates that is entrained with the impactor core. So we can predict the volume of silicates that is entrained and equilibrated with the impactor core as a function of the impact velocity and the impactor size. So what does it mean for planetary impact? So if we take the Froude number of a giant impact with a Mars-sized impactor, we predict a quite low Froude number, and so we predict that the impactor core mixes with less than 1 time its volume of silicates, so quite low mixing. Whereas now if we take a 200-kilometer impactor, it mixes with almost 100 times its volume of silicates, so extensive mixing. And so here I can predict the volume of silicates that equilibrate with the impactor core. But now if I write a mass conservation equation and I assume that the impactor, the entrained silicates equilibrate with the impactor core, you can basically easily predict the mass transferred between the metal and such silicates. And so from this scaling law, we can predict the degree of chemical equilibration after an impact. So to conclude, I hope I convinced you that our knowledge of the core has progressed or has improved quite a lot during the past 100 years. And I showed you among the first experiments, analog experiments that can model the impacts that form the Earth, the large impacts that form the Earth. Those experiments can produce small scale and turbulence, and so we think we can quantify chemical transfer. And from those experiments, we obtain scaling laws for chemical equilibration between metal and silicates. And we predict more than 5 times more equilibration than previous models. So these new scaling laws are going to have very important implications for the composition of the core. And so there are many open questions. One of them is that here I consider that the entrained silicates equilibrate with the entire impactor core. To know whether that's correct, you need to actually predict the size of the metal drops in the magma ocean. And that's a topic I'm currently working on using immiscible liquids. Another important question is, how does, can we predict the initial composition of the core? And especially, can you put enough magnesium and silicon in the core to actually power the dynamo by exsolution of those elements? So thank you very much for your attention, and it's a pity that the movies didn't play. Thanks.
Okay, in the next 5 minutes, I'd like to restrict my subject to one question. Can we predict the intensity of the magnetic field of a planet, knowing its radius, its planetary rotation, or the electrical conductivity of its core, or the power available? As physicists, we use an energy balance using the ohmic dissipation to relate B to the square root of the available power, P, in this slide, and taking the Earth core value, we can predict with such an equilibrium a magnetic field of 1 Tesla, way too high to the 1 millitesla value according to expecting at the top of the core. A way to solve this discrepancy is to introduce a planetary rotation. So let's have a look to the dipole moment on the y-axis here of the planets of our system. There is a clear dependence of the rotation rate, but observations are ambiguous to determine how rotation enters the physics. And we will follow Elsasser, 1946, which introduced a force balance between Coriolis and Lorentz force. You have the Coriolis force, omega cross U, balanced with the Lorentz force, G cross B. And if you play with it, you find that B, the amplitude of the magnetic field, should scale as the square root of omega. And if you take the value of the Earth core, you find that B is 10 to minus 3 Tesla. Bingo, this is the value, expected value of the top of the core. So we introduce the Elsasser number, big lambda. And if the Elsasser number is 1 or larger than 1, then you go into the strong magnetic field, or what we call the magnetostrophic balance. The problem is that the Coriolis force is not working, and it's not bringing energy into the magnetic field because it doesn't work. So we need to rely on another force, working force, to maintain the system. And generally, people introduce the buoyancy force, which is the Mach balance, magnetic Archimedean force. And this is really what is the true quest of geodynamo modelers. Here, Christensen and Ober plotted the Elsasser number on the y-axis as a function of the magnetic Reynolds number, and the x-axis, magnetic Reynolds number, which measures the dynamo process. They did form strong field calculations with large Elsasser number, so that's good. But we observe no change at Elsasser number 1, and no change between weak and strong field. So, according to this calculation, the Coriolis force do not control the saturation of the magnetic field in geodynamo models. It is the buoyancy which controls the magnetic field B on the y-axis here. You can, the x-axis is the modified Rayleigh number, which is a measurement of these buoyancy forces. And this leads to a magnificent power law with a coefficient exponent which is 138. But the problem is that on the y-axis B, there is a correction factor, which is the relative fraction of ohmic dissipation, and this is dependent, model dependent, which is not satisfactory. How can we progress? There is two ways. The first one is to revisit the magnetostrophic balance and introduce a magnetic modified Elsasser number depending of delta. Delta is a scale, and then now the magnetostrophic balance becomes scale dependent. Or the second path will be a better scaling of the Mach balance. And for example, Davidson in 2013 introduced a vorticity argument, which shows that now the magnetic field has a power 1/3, very close to geodynamo simulation. But again, this second possibility rely on geodynamo simulation, which are probably not very relevant for geophysically speaking. So I would like to consider more a local approach, which I want to illustrate here with a calculation of Nathanael Schäfer. There is places in the core where the magnetic field is strong, and then you have 3D magnetostrophic flow, which are in the Mach balance, what was described by Julien Aubert. And there is places where the magnetic field is very weak, where you have the magnetostrophic balance, but a quasi-geostrophic 2D flow, and where the turbulence replaces the magnetic field. And I hope following this, we will be able to predict what is the amplitude of the magnetic field of a planet given its input parameters. Thanks.
Good morning. Once my talk comes up, I'm going to talk to you about how we know what we know about the magnetic field from observations. And there are my slides. So what we know depends a lot on the timescales we are looking at. For the recent years, we have good satellite observations. For the past decades, we have a network of global geomagnetic observatories. Further back in time, we have historical observations and documents. And if we want to know about the magnetic field even further back in time, we have to rely on information that is preserved in materials like archaeological artifacts, volcanic rocks, or sediments. And once we have a compilation of global measurements, be it the good global coverage that we get from the modern satellites, or even the sparse coverage that we get from paleomagnetic data, we can apply mathematical inverse methods to determine magnetic field models that fit the data. And the widely used method of spherical harmonic analysis has the advantage that we can map the field not only at Earth's surface, but if we assume that the mantle is insulating, we can downward continue that model to give us an impression of the magnetic field morphology and of the magnetic flux at the core mantle boundary. And this provides a lot of information about the fluid dynamics of the Earth's outer core. For example, we see in the magnetic field that there are patches of magnetic flux that have an orientation opposite to the dominating dipole field. We find patches of flux that drift strongly westward along the equator, and we find patches of flux that are more or less stationary on short time scales of intense flux at high latitudes. Also, symmetries or asymmetries that we find in the field give constraints on the operation of the geodynamo. For example, we see that the magnetic field is more variable and the secular variation is stronger in the southern than the northern hemisphere in today's field, but also on longer time scales. Now we have these type of continuous models for the past thousands of years, back to 100,000 years, but it becomes more and more of a challenge the further back in time we go. So what we can also do is look at time-averaged models that give us more of a statistical information about properties of the magnetic field. For example, we see if we look at field averages from thousands of years to millions of years, that the field does not average out to a simple axial dipole, but always some non-dipole contributions remain. But on the other hand, we also see that there are some preferred patterns of magnetic field morphology. An intriguing feature of the geomagnetic field is that it occasionally reverses its orientation completely, either in short excursions or in longer-term magnetic reversals. And we are starting to get first global pictures of these events too with the data we have presently available, like in this example of the La Chambre excursion 41,000 years ago, or in some excursions that we see in the model of the past 100,000 year field. But getting a detailed and good global picture of these extreme events remains a challenge, as the data coverage remains sparse, and it's a big challenge to obtain high-quality data in the lab and to also get independent ages, which are mandatory to obtain meaningful global models from that. So, in conclusion, these global models are a very useful tool to provide information on the workings of the geodynamo. They are also useful in interdisciplinary applications to estimate the shielding of the geomagnetic field against solar wind or galactic cosmic rays. But we need more good observations on all time scales to answer some open questions. For the present day field, we need highly accurate observations to be able to distinguish better between the magnetic field that comes from the Earth's core, from the Earth's interior, and fields that originate in the ionosphere and magnetosphere, with their applications or with their relevance for assessing space weather hazards. And on the longer time scales, we really have to get a more detailed picture on all the long time scales, including these extreme events, to know better how the geodynamo really works and to become able to predict how the magnetic field will evolve in the future, to understand what the driving mechanism behind excursions and reversals is, whether it's a distinguished mechanism or all are just part of a continuum of axial dipole variation, and to be able to predict when the field will go into its next excursion or reversal, even though that will be definitely at least a couple of centuries from where we are now. Thank you.
Hello. So we've heard about magnetic field measurements and the fluid dynamics in the core which generate the magnetic field. Now I'm going to zoom in on the material properties who actually allow for heat transport and magnetic transport in the core. We've known for some 67 years that the core is made up of mostly iron, but the inferred densities and seismic velocities through the inner and outer core require that there be about 10 weight% of light elements alloyed in. And as you can see on this left-hand side plot, a really sizable number of publications have since then argued for specific light elements. And we care about ascertaining which of these light elements is actually in the core, for one, because their preferential partitioning into the liquid outer core during solidification of the inner core provides a really efficient buoyancy source for driving convection in the outer core and hence for the geodynamo. But growing consensus that the inner core is young, coupled with the fact that we have evidence for a magnetic field on Earth for over 3 billion years, requires that the heat flow within the core be more than that which is conducted along the adiabat before inner core formation. And this is challenging given trending high values for thermal conductivity of iron in the core. While initial measurements or initial guesses for the light element in the core came mostly from measurements of elastic properties of solid iron compounds, solving this dynamo mystery really prompted a transition to more chemistry-focused experiments. And while high-pressure experiments of all kinds of varieties have been going on for more than a century, laser-heated diamond anvil cells have really emerged in the past few decades as powerful tools to let us probe the chemistry at relevant core pressures and temperatures. In these experiments, a small sample of iron alloys compressed between the tips of 2 diamonds to high pressures and subsequently heated and melted. We then quench the samples from high pressures and temperatures and use various analytical tools to probe texture, composition, etc. of the quenched melts. And doing so has led to reveal a lot of complex phenomena that come out from melting these alloys. Several recent high-profile papers have revealed that magnesium is soluble in iron at the ultra-high temperatures conducive to giant impact conditions. As the core cools, magnesium becomes insoluble and crystallizes out of the core as MgO. Another study revealed that silicon and oxygen may not coexist in an iron alloy melt and instead form SiO2. Both of these phases are really buoyant with respect to iron, so they also provide potential sources for driving an early dynamo before the inner core. I've also found that these experiments can lead to liquid metal immiscibility that persists to the pressures of the core. In these experiments, melting of iron alloys containing silicon and oxygen resulted in the quenching of 2 liquids, one which is oxygen-rich and one which is oxygen-depleted. By mapping out the textural evolution of the samples, we were able to measure out the miscibility gap in pressure-temperature space, such that when you're in the gray region, you have 2 different melts making a layered core, and when you're in the dark green region at higher temperatures, you have a single liquid core. And this has implications throughout Earth's history. An early Earth hot geotherm may lie entirely within the miscible regime in dark green. In this case, you have a homogeneous single liquid FeSiO core. Today's core geotherm probably looks a little more like this colder one, which lies entirely within the immiscible regime. In this case, the oxygen-rich liquid separates and is buoyant, so it collects at the top of the outer core, forming a stable layer, something which is also observed seismically and inferred geodynamically. An interesting case happens in an intermediate scenario where the geotherm crosses the miscibility closure curve deep in the outer core. Because of the pressure and temperature dependence, the melts demix first from the bottom of the outer core, and they continue to demix and remix, pushing this dashed boundary between the liquid layers up and down temporally. And you can hear a little more about this story of immiscibility, which could potentially power an early dynamo later this afternoon. So to conclude, the trend of mineral physics experiments towards looking at interactions between light elements has revealed phenomena like crystallization of silicates and oxides out of the core into the mantle, as well as liquid immiscibility, both which can provide a potential source for an early geodynamo. Moving forward in the next 100 years, but hopefully sooner, we'll be answering some questions like what are the implications of immiscibility in the core, both for early Earth and today, whether there are observables produced from crystallization of silicates and oxides out of the core into the mantle, and why we haven't yet come to a consensus on the values of thermal conductivity and the melting temperature of iron in the core. Solving these questions will be essential to our understanding of the composition, structure, and thermochemical evolution of the core, and hence the geodynamo.
All right, I'm Kei Hirose from Tokyo, and I'm talking about SiO2 and molten silicate release from the core with implications for dynamo and material transport from the core to the mantle. The core convection and geodynamo has been driven and sustained from the early Earth. Now we have inner core crystallization, which provides sufficient power to drive core convection. But before the birth of the inner core, the core convection should have been driven either by thermal buoyancy or chemical buoyancy. Right? So the recent findings of possibly or likely high thermal conductivity of the core makes thermal convection very difficult. And this is the summary of the recent result of core thermal conductivity. And as you can see here, it is very, very controversial. And some experiments and theory show the very high values for the core thermal conductivity, while the others show the relatively small numbers. But if the core thermal conductivity is high, then the thermal convection with high conductivity means rapid core cooling, and resulting earliest core mantle boundary temperature may be too high. The alternative way to drive core convection is compositional buoyancy. And first of all, the original core composition may be enriched in silicon, oxygen, and magnesium as a result of high temperature core formation. And this is the simulation by Oroki and Stevenson, showing the original core composition is enriched in silicon and oxygen as well as magnesium. And Oroki and Stevenson and Bardo et al. Suggested the SiO-Mg rich core absorbed MgO, and which the MgO extrusion powers core convection and the dynamo. And more recently, our group has proposed the Sio2 extrusion from the core. And this is simply based on the limited Si plus O simultaneous solubility in liquid iron, which has been very well established at 1 bar, as shown here, for steel-making purposes. And our high-pressure experiments showed it is also true at the core pressure range. And this is our latest experimental result by using the small size of sample in order to minimize the temperature variations across the sample. And now the sample size is only 7 microns across, in which we have only the temperature variation of a few tens kelvins. And even so, we have, SiO2 crystals right in the middle in the liquid iron, showing that this liquid is saturated with SiO2 and therefore crystallizes SiO2. And this experiment was performed at the core mantle boundary pressure and temperature. And as we discussed before, SiO2 extrusion also powers core convection and the geodynamo. Right? And more recently, we have examined the joint SiO2 and MgO saturation in the core and found that it causes extrusion of not only SiO2, but also the silicate melt. I would like to remind you, if you have both MgO and SiO2, then the MgO and SiO2 have a eutectic system in which the eutectic temperature is less than 4,000 Kelvin at the CMB, for the SiO2 rich part. Right? And okay, so the pink region indicates the composition of the silicate expelled from the core. And such composition, okay, so this is a ternary diagram, MgO, FeO, and SiO2, the liquidus phase diagram. And this liquid must evolve to the iron-rich side, FeO-rich side, over there by fractional crystallization. And as eutectic temperature is less than 3900 K, such silicate could be still present as melt above the requirement boundary, which may be responsible for the ultra-low velocity. Thank you very much.
Okay, well, this is not the right slide. Hopefully it will be soon. But I just want to round up the Dynamo session this morning by discussing where we are with paleomagnetism and direct observations of Earth's ancient magnetic field, and where we need to go next to actually constrain the oldest record on Earth and really understand what our magnetic field means for habitability, if my slides appear. I can keep going. So basically, right now, we have a relatively good record of Earth's magnetic field from rocks that are currently on Earth's surface until around 3.5 billion years ago. Before that time, it becomes much, much more challenging to actually get a record of Earth's magnetic field from rocks. And this is actually the critical time period, here we go, for understanding what our dynamo was doing, as I will now show you. Okay, so we've talked about, well, let's go back to this. So why do we initially think that Earth's magnetic field is actually important for habitability? And there are several reasons, including the fact that it provides this protective shield around our planet, which protects us from cosmic radiation. And it's also thought that our magnetic field allows liquid water to be stable on the surface of Earth. And so it's been hypothesized that perhaps why Mars did have liquid water on its surface but no longer does is because its dynamo switched off billions of years ago. So this is the record that I was discussing about the record of Earth's magnetic field going back through time, until 3.5 billion years. And as I said, this is from whole rock observations. The reason we want to extend this record back in time is actually to see what was our magnetic field doing when oceans first formed on the Earth, and then when life first started to develop. And until we understand the relationship between the two, it's very difficult to know exactly how important magnetic fields are. So why is it so difficult to fill in the record of the magnetic field this far back in time? Firstly, the yellow dots on this map show where there are Archean terrains left preserved on Earth. So these are the most ancient rocks we can find on the surface. When we go back to the Hadean, there are no records left in rocks, only crystals. So firstly, we have to target one of these very few terrains. Secondly, these terrains are heavily overprinted by metamorphic and metasomatic events. So what that means is that the primary magnetic minerals that formed in these rocks are very likely to have experienced future events that may have altered or overprinted their magnetic records and make them very, very difficult for us to interpret. Once we actually get to one of these ancient terrains, so this is a photo of us doing paleomagnetic research in Sio2 in southwest Greenland, and if you would like to hear more about this specific project, please come and hear my talk this afternoon at 4:15. But even when we actually get to one of these terrains, it's actually still really challenging to get one of these records. So firstly, a lot of the traditional paleomagnetic field tests we use actually don't work so well, so we get ambiguous results rather than a concrete pass or fail, which tells us about how well preserved these rocks are. Secondly, many of the lithologies that are preserved in these ancient terrains are just not very good paleomagnetic recorders. So when we measure them, we get very unstable signals. And thirdly, in order to understand when that paleomagnetic signature was recorded, we need to understand these highly complex geological histories that have developed over billions of years. And so these are challenging to interpret while we're in the field and then in the measurements we make back in the lab. And so in order to progress our field further and to really capture a record of the geodynamo going back in time, the paleomagnetists in our community need to start using novel and different techniques. So things like single crystal paleomagnetism, which is a pioneering technique where rather than looking at a whole rock sample, you literally extract individual crystals from a rock and measure the magnetic signals recorded by those. So for example, this is work that's been done in the Jack Hills zircons in Western Australia. We also need to look at ancient rock types, such as banded iron formations, that don't form in the present day. So it's hard for us to understand exactly what record they show. But we really need to understand how these ancient mythologies record a field and whether they show us reliable paleomagnetic information. In addition to measuring and using these pioneering techniques, we also need to start using very high-resolution microscopy techniques to understand exactly where the source of magnetization comes from. So this is a paper that came out last year on the Jack Hills zircons. So you can see a zircon crystal here, and then the magnetic inclusions which are carrying the magnetic signal. And this very high-resolution study shows that actually these magnetic carriers are secondary. So they're not the same age as the zircon crystal. And now the challenge is not only figuring out how old they are, but also when they recorded a record of the ancient geodynamo. And so to conclude, in order to understand the role that planetary magnetic fields play in habitability, we need to know what our magnetic field was doing when oceans first emerged on Earth's surface and when life first took hold. In order to do this, we need to start using novel and pioneering techniques in paleomagnetism. And these must include microscopy to fully characterize the magnetic minerals that are recording the signature, magnetic microscopy to identify where the magnetization is located in our samples, detailed petrologic context to understand those metamorphic and metasomatic events, and then targeted geochronology to date the exact age of the magnetic carriers. And with that, I'll finish. Thank you very much.
So apparently we have room for one question. So is there any question in the room? I'm not the one restricting the number of questions. Yes?
This is somewhat of a general question for anybody who wants to take it, but I'm wondering what we might learn from the Psyche mission going to visit ancient core of a disrupted protoplanet, which shows some evidence for silicate on the surface of an object which is inferred to be dominantly iron nickel.
So Sarah and Kay, do you have an idea?
I mean, I'm not sure if we'll be able to get any kind of optical type images from the mission, but personally, I would be extremely excited to see any kind of these miscible textures, whether it's between iron alloys or between potentially metal and silicate being miscible.
Okay, so my favorite core element is the hydrogen, right? And but hydrogen escapes from the solid iron at relatively low pressure. So I don't expect any evidence for hydrogen, but I do believe hydrogen is present in the Earth's core.
Thank you very much for your attention. So I think I'm supposed to close the session now. No music? Yeah, apparently there is no music. Philippe is complaining. So thank you very much for your attention, and thank you to all the speakers for their great talks. Thanks.